Hello, everybody. Welcome to my podcast. Today, I am here with Michele Iuliano, a structural engineer who is going to bring a little bit of his experience to us and who has worked in many different projects, who has a huge experience to share with us. Iuliano has worked internationally in quite a few countries with different type of structures, and I will, well, nobody better than him to tell us the countries and structures that he has developed. I will now let him talk. So long story short, Giuliano, welcome to my podcast.
Thank you so much. Thank you for having me. And good evening to everyone. Good evening, good afternoon, good morning, based on where you are connecting from.
Nice, thank you, Giuliano. So let's begin talking about the projects and countries that you worked on.
Well, I mean, just a brief description on who I am. Senior structural engineer from Italy, graduated few years ago now. I started to work in a small firm in my hometown, but then I decided that that one was not the thing that I wanted to do. I wanted to explore the world. I want to challenge myself with other stuff. So I focus always on putting myself outside the small boundaries that a very small town in the south of Italy can give you if you don't push yourself. So starting from moving outside my small town, I went to work for a big engineering firm in the north of Italy, middle size construction of engineering firm in the north of Italy. Spent a bit of time there, and this one allows me to have the first approach with the international project. The national project means a project that has been done all over the places except in Italy. Pretty much.
Right.
So my very first project was a seismic design of a multi-story building, and it was apartments, 7 floors, and 10 stories, 10 bays, roughly. The idea of the project was to construct a new basement, to lift it up, put some bearings on the new foundation that they were building, lift it, just lower down the building and base this building on these bearings. So without damaging or without trying to damage the building itself, it was a full lifting, replace the bearing, put it back. That one was pretty interesting project. Then the first real experience was with some viaducts in Riyadh and in Algeria, in which we design a precast concrete viaduct for these places. Pretty interesting project. The top of the apex of that part of my life was when I was involved in the construction engineering of the new safe confinement for the Chernobyl power plant that exploded in 1986. So exploded in 1986, yes. And they covered with a temporary safe confinement in order to avoid any spread of radiation and radioactive dusts. Of course, that one is an exclusion zone, controlled by the army at the time. And the idea was to have a new safe confinement, so a mega structure of in steel, cladded with lead in order to avoid that the radiation would escape from that. 236-meter wide, 230 high, unmovable structure. So because of the constraints of the site, the structure could not have been built directly on the power plant, but has to be built about 100 meters away from the power plant, and should have been skidded or pushed on top of the building itself. That one was a very, very, very interesting project. And they
And
had
it was your first,
spent.
second project.
No, that one was a while, but it was my first project in which I worked on site,
Okay.
in which the client asked me to be on site. So I spent about 11 months in the construction company office on site, with a winter of minus 40 degrees Celsius. Uh, so it was pretty rough, but an unbelievable experience. Then I moved to United States for a while, working directly on site for a big company, managing the construction that they have to do there. Uh, and then I went back to Italy. Then I moved to Australia for a while in Perth for the bridge that they built in Perth, the Matagaru Bridge, the new bridge that is connecting the two rivers um, of the river that is the two banks of the river that is passing through the city. It's connecting one side of the city with the big stadium that they built on the other side. Very interesting project as well.
Juliana, do you have
Back
photos of these projects that you could share with us?
Yes, I have. How can I share those things? First, well, I mean, let's get some photos from internet. Let me share. How can how can I share my screen?
You just need to press present at
Present,
the bottom.
yes. Okay, found it. Share screen. Share screen. Which screen is sharing here? Oh, okay, we need this. Share. Alrighty. Now, when I talk about the new safe confinement in Chernobyl, I'm talking about this little guy here. So this is the new structure that they have done, and here you can see some of the construction. So what I meant before was here you can see on the side the power plant. The structure itself has been built about 100 meters away from the structure, and if you can see here, there are some rails in which the structure can slide. You can
I
see
can't see
here,
the rails.
because it's a little bit difficult to see. Let's see if I find a better. Here we go. Probably this one is the best photos. Let's see if this one is. All right, they're a little bit difficult to see, but here, you see here on this side,
No,
Leandro?
I can only see the
Can you
trusses.
see this one? The two red lines. The two red lines.
Um,
Can you see the two red lines?
no, the only red lines that I can see, they are the trusses.
Which trusses are you talking about?
Yeah, those ones you are showing now, where you, if you go to the right up, yeah, those trusses.
Which trusses?
Well, I can see a image of many trusses together, and then on the right, probably the tensions are bigger. If you go to the left, they become green, light blue, and blue.
Green, like blue and blue.
Are we looking at the same thing? I will
I
send you
don't
a
think.
photo. I'll send you
Yeah,
a photo of what I am
yeah.
looking at.
No, 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 not this. No, 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 no. It's not this. How can I thought that? Hold on. Let me stop sharing this thing. Present again. Was not that one. Share screen. Share screen. This one. Share. This one here. Can you see that?
Oh, yes, I can.
Yes. Here we go. So this one is the new safe confinement in Chernobyl. Here, this one here is the power plant. This one is the cooling basin that they use for cooling the power plant as well. And
Sure.
what I was mentioning here, this is the power plant. So this structure has been built far away from the power plant itself,
Yeah.
because what was the problem here? A huge amount of radiation, so nobody can work here for more than 2 or 3 minutes. So what they had to do is to build the full structure outside the range of the radiations, and then skid to move to slide the structure all the way on top of this rail of this structure. So this one was pretty much the new safe confinement. When I was on site, one of my tasks, beside the all the temporary works engineering that I had to do, uh, I completely redesigned this portion of the structure itself, this cantilever here, and
Yeah.
the support for the vent stack.
Mm.
This was the project here. Regarding the Matagaru bridge in Perth. Are you still watching that?
Yeah,
Can you see the bridge?
I can.
This one is the bridge in Perth. Now, on this, I didn't design the bridge itself. I was not involved in the design of the bridge itself. I was involved in the design of the small the short span on the side, and in all the temporary engineering. So all the methodology in which these two arches has been put together, assembled on site, transported with barges in position, and then lifted up.
Um,
And this one was in Perth. Yeah.
okay, I have a question in regards to the difficulties that you
Hmm.
faced when you were doing this project.
Difficulties. Well, okay. So imagine that you are pretty much a fresh engineer in uh, in a completely new environment, working with a client that has a very strict schedule, something that has to be done and that's to be done quickly. So everything can be committed in, you know, hours. The pressure is very very high. The pressure is very very high. What is the good side, the advantage of that is that usually you are you are the expert. When they call you there, you are the expert. So they ask you to perform technical things, and you have a series of a team that can work for you, that can help you out. So you don't have to carry out the entire work alone. But yeah, the difficulties are to be in a new environment, in a completely different situation. When you are on the other side, I like to call this to be on the other side of the barricade, because usually the structural engineer is sitting on the desk preparing its design, and there is no much pressure from the construction company if you are not involved in the construction engineering. While you are on site, you are on the front line, so you have to deal with a very strict schedule and the pressure of being on site. And every moment that you waste is a waste of money for the company. So there is a very, very, very huge pressure from
How
this
did you
point of
deal
view.
with that?
You just try to do your best and work there, focus on the task that you have to do, and give your 150%, nothing more. You have to be 100% focused, you have to be 100% on top of the task that you're doing. Even though you are not you don't know how to do the task, there are people that can help you on managing the problem. Because of course, if you are the first time, for the very first time in a construction site for a project like this, there is absolutely 95% of the tasks that you will face there is part of a task that you have never seen before. So there is nothing that can prepare you for these kind of things.
Nice.
Above all,
Only,
the very first time. Huh?
yeah, the only thing that is going to prepare you is to go there and do it.
Yeah, the only thing that can prepare you is to go there and do it. I mean, exactly right. At the end of the day, you have some knowledge, you have some conglomerate of cell in your head, in your skull, and you have to use it.
Yeah, that's right.
Yeah. So that's the main thing. There is nothing else that you can do. When I went the very first time in Ukraine, there was another guy with me, an experienced engineer. He spent 2 weeks and he ran away from the site because it's not a life for everyone. We used to wake up at 5 in the morning, 5:30 in the morning, be on site at 7 after 1 hour and a half of ride on the car, checkpoints, police control, military control. In a difficult environment, usually you go back around 7:30 if you were lucky, 8:30. That one was the case every single day, Saturday included. So it's not a life for everyone, but if you can cope with those things, and if you are determined in the things that you are doing, the reward is extreme. At the end of
So,
the job in Ukraine, the company gave me a bolt. This bolt was numbered, so was labeled with a number, and those bolts have been given only to the high management of the project. So I'm only one of the few person that has that bolt, and
well done.
that is
Congrats.
something to be proud of.
Wow, congratulations, Iuliano.
Yeah,
Like, when was it? When did you go to the
Chernobyl
Ukraine?
2016.
2016.
Yes. All
Okay.
2016, the 8th of January 2016, and I came back the 1st of December 2016.
Yes, I feel like you were going to a war.
It was when I arrived there. I arrived in full winter, minus 30 degrees, 40
Minus
degrees.
30.
minus 30, minus 40. The winter was pretty tough there, but
Man, I
was
was
not.
I was I was complaining because I went to Melbourne a while ago, and I got -4.
But I have to tell you something. That one was not the toughest winter that I found. I have been in United States, right, in Michigan,
Right? Yeah.
between Chicago and Milwaukee. And the winter that I spent there, we reached temperature of minus 62 degrees.
-62.
For 3 days, there was a temperature that were oscillating between minus 58 and minus 62.
Okay.
So yeah,
Wow.
that that that
-68.
that's that was tough as well. That was a tough winter as well.
I can't
So
imagine.
yeah, so those are pretty much the projects. What's up?
Welcome back. I think that you closed the window.
All right. Anyway, so yeah, those
Okay.
were the two main projects that I worked in 2016 and 2017.
Nice.
Um,
You mentioned that you went to North America. Do you have any uh, photos of projects that you worked there?
the project in North America was pretty much to follow the construction of a warehouse. So
Warehouse.
don't think. Let me see. Seda North. Let me see. I don't think. Okay, yes. The warehouse was this one here. Let me share again. Let's see. Present. Share screen. Share the screen. Southern North America. Okay. This one was a warehouse that we were building. So I went there to follow the construction of this warehouse.
Okay. So it was just a warehouse. Oh, that's a
Yes,
big
it was.
warehouse, though.
Yeah, no, it is a big warehouse. Actually, this one is about 450 meters long and should be 200 and something wide. So pretty big project as well.
And what was your role there?
Uh, construction manager,
So
site
you did
manager.
not work on the design.
No, I didn't work on the design for this. No, 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 no. For these things, there were some. You know, when you are working on site and you are the only engineers, of course you have to design bits and pieces here and there for what they required. So if there is a modification here and there, but no, I was not involved in the design itself. I was involved more in the managing the work site.
Okay.
So yeah. So yeah, I mean this one was between 2017 and 2018. We are still far away from the present time. I don't know if you want to go on with this or
Yeah,
we
let's.
stop
Well,
we stop bothering the audience.
no, 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 no. I think that the audience is gonna be really happy to see the projects that you worked on. Like from 2018 to we are in 2024. Jesus, that's a lot. How many projects did you work on?
Well, 2018, I worked on a after the United States, I went for a while in India for the construction of
India.
Yes, there was a modification of a five-star hotel,
Can
and they
you
had to.
do? Do you have photos of that hotel?
This one will be a little bit tricky. Let me think. Tecnostruttura. So this company here that I'm about to show you, let me see. When we will go with a more recent project, we will show you this.
Which one?
This one would be a little bit tricky. Technostructura. Because what this one was a company that has this system. I'll show you. So what they do with this, yes. So what they do here, they have this particular system. So they design and they construct this system. This one is a tube, a steel tube, in this particular case, a steel tube that will be filled with concrete, right? So there is a reinforcement inside, a steel tube outside, and on site it will be erected as a normal column, steel column, and then we will pour with concrete. And as you can see here, there are also the beams, the same thing. So you have a lower level, a lower part of the beam that is in steel plate, that is used to be the formwork for the concrete itself. Then you have the reinforcement inside, and here you will pour all the concrete in order to solidarize the steel beams with the columns, and everything will work as a composite structure itself. So this
How
is the
wide?
system. Hmm?
How wide are these beans? Because they look really big.
This one can be 1.5 meters. That
1.5
can be.
meters.
Yes, yeah, those are a huge thing. Those are huge beams.
Okay.
It depends from those one are some of them are smaller, but some of them are really huge. Um, so this one is the system that they developed, and I was on site for them to build. Let me see if I hotel New Delhi Technostructure. Let's see if I found. Yes, okay. Yep. So now the hotel is this hotel here. Can you still see the
Yeah, I can.
right? Yeah. So this hotel here. Now from this side you cannot see, but on the other side behind here, they constructed a full new part of the building, and they have to build this over this wing of the building here. So what they have to do is that all the things that were above this level, they had to be supported by this system,
Okay.
and they needed to have some seismic isolator to avoid a big impact on the foundation of this. So what I was involved in was the level in which they created this transfer floor, in which they put some isolators all the way up, and I was involved in following the construction there for this part. for this portion. Yeah, this is the building. Let's see if I can find the portion of the building that they built afterwards. Maybe here. Let's see. Yeah, here we go. This one. Can you see here?
Well, I can see one,
Hold on. Let me see.
which is pretty much the one you were showing. Oh, yeah, I
Okay.
can see that.
Can you see the model here?
I
The
can.
violet model? Yeah. So this one was the structure that I was talking about. So they built this part, they reinforced this part. Then here they had a big transfer floor, and from there they built all these things up.
Okay.
So that one was a pretty interesting job as well. Pretty interesting. You see here. Here we go. Was the construction. Zero security, security, zero safety.
Zero safety. You
That
were the
that was.
construction manager.
I was the engineer on site. I was not a construction manager. So there they don't have a safety guy. So yeah.
Okay.
Now here on this you can see the net around, but the net around, they put the net around only to take this picture. The net was put only and only for taking the picture.
Really?
Yes. Yeah.
Interesting.
Yeah, very interesting. So yeah, this one was the other project in New Delhi. Then after that, I moved to Australia, and that one and there started my adventure in Australia. We are talking about now
Perth,
2019.
which was Perth, the bridge you showed us.
No, that one was 2017. Then I went to United States, New Delhi, and then I came back to Australia, to Sydney. And from there, I never left Sydney.
And what type of projects have you worked ever since?
Okay, my very first project that I worked in Sydney. Here I can show you something a little bit more interesting.
Okay.
So open my very and actually this project here that I'm about to show now is a project that I started to work when I arrived, and now they are retaking this project as well. So they are working on again, and I'm involved again in the project. So let's see. Where is it? Here we go. You see this is a SAP model. It's a SAP
Um,
model.
no, I can't see anything. You need to share.
Can you see now?
Oh, yes, I can.
Here we go. Yes. So this one is the sub model of the roof that is of the stadium that is called right now Accor Stadium, is in the Olympic Park. This is the existing roof. So the east and west portion of the roof with a main arch, and the south, north, and south portion of the roof that are two temporary roofs. Now, when I arrived here the first time, I worked on this stadium. I was involved in the roof, but at that time we were developing a fully new project of the stadium itself. And I was the coordinator for the steel part, for all the roof stuff. At this stage, we are doing this in parallel. We are developing a new proposal for the new roof, but we are proposing also to maintain the existing roof and to strengthen in order that the existing roof can be maintained safely for other 50 years. So this is the type of work that I started with. Of course, I mean, in 4 years that I'm here, not all the projects are on this level of, because this one is a big project as well. Not all of them are big projects like this. But since I started to work here, I worked on four stadia,
4 stations.
four
So
stadia. Yeah.
you have been only doing stadiums.
No, I've been doing Stadia. I've been doing cable stayed bridge. We designed a cable stayed bridge. We designed a via ferrata. Do you know what via ferrata is? Via
No, I
ferrata
don't.
is imagine a path on a cliff in which you have to climb, anchored to a rope or
Okay.
to a stairs. We have rather something like and we design all the anchors in this one of this structure, and we were designing this, and now they are building the thing in Queensland, in not so far from from Brisbane. So we
Okay.
designed that, um,
What is
and then
related
small
to? What
stuff.
is it related to? Sorry, I don't know what that is.
Hmm?
Um, I don't know what that is.
What is this? Yeah,
Is it a climbing thing?
it's a climbing thing. Imagine that you have a series of obstacles like the one here. Let me share again. Share screen. Imagine that you have a series of obstacles like this, for example,
Oh
a
yeah,
rope like this, all these things on a cliff. You have these kind of things, no? And we
yeah,
design a full park of these things in Queensland. Imagine something like that.
yeah.
Ferrata. Let's see if yeah, the project is been built now, but this is the layout of the project. Let's see.
Nice. S- So the job was pretty much to design the hooks.
And then the job was pretty much the job was pretty much designed. Now in there are some bridges. So some bridges, some small pedestrian bridges.
It's cutting. Hello.
Yeah, I'm here.
Your internet's cutting.
Yeah, I know. So yeah, as I mentioned, I don't know when you arrived, but in that we designed the ropes, we designed some platform, we designed some bridges, some stairs, these kind of things.
Okay,
Small
nice.
things
Everything.
here and there, but very, very, very interesting project because very unusual.
Okay. Yeah, I guess so. So what of
Yeah.
I think that every single project got you somehow.
Well, uh, I well there are well one of my favorite projects of course was the project in Ukraine, but since then another one that took me and I'm still working on is a stadium in New Zealand. We are doing the construction engineering of this stadium. and I'm the lead designer of the construction engineering for that stadium. That's pretty interesting job, pretty demanding because the contractor is from China, and there are some barriers in language, and there are some barriers in organization. But yes, it's pretty interesting
So
as well.
your co-workers, they were Chineses, were they?
No, the construction company, the
Was
steel
Chinese?
fabricator is Chinese. Yes.
Okay.
Yeah. No, the designer. I was the lead designer, and the team is pretty much Italian, and we have
Okay. Well,
some
so
Australian here. Yeah.
okay, so it was easy to
Yeah.
be
To
with
communicate with
the
the
office
team.
team.
To communicate with the team, yes. To communicate with the client, a little bit different, but
Okay.
we
Right.
manage.
Now, yeah, I guess so. Now, Giuliano, I would like to turn everything is a lot of theory. I wanted to invite you to design something for us in life right now. Can what can you design, and what would you be able to 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 analyze?
Well, I mean, I think that's an interesting project to see because it allows you to see the different aspect of what the design is a small bridge. Now we will go with a very simple structure, but here we don't have to go in we don't have to design fancy things. We have to understand the principle. So if you want, we can go we can dive straight um, in a small bridge, truss bridge, steel
Okay,
bridge, and
let's go
we
for
we
a
see what's the and we
let's go
see
for
what's the process.
a bridge made out of trusses.
A bridge made out of trusses. So first of all, let me share the screen. Window. Oh, here we go. File. New model. Not save. All right. So do we have to go? Do you want me to go in all the steps by step, all the choices that I'm making on this, or do you prefer to do more high level on the geometry itself, on the modeling itself, and then to focus a little bit more on the design? How do you want to approach this?
I will leave it for you as an expert. Just bring whatever you think that is valuable for us.
Well, I mean, you know what they usually say. If you know how to do something, don't give to your client everything in order that he will call you again, right?
Right,
So
right.
the point is, I will give you just a flavor on what it could be, and we will organize another podcast to go more in detail.
Okay, right.
What do you think?
No, that's a good point. I think that I will leave also this point for my audience, and I will ask all of you who are watching, what would you like to see from Michele Iuliano in my next podcast?
Yeah, I think that
Just
if
leave
they
a comment below, and let's work on this together. Because right now he has put it on us, right? Let's get back to him with something interesting.
if they are not sleeping yet, for the moment I can give you just a brief introduction. But next time, if your audience is interested in, we can see how we can link a parametric modeling with the Rhino Grasshopper into SAP and design parametrically a structure.
Nice. Sounds really good.
So for the moment, let's go with basic stuff. So first, when we start with the basics, we have to start with the basics. So what is a bridge? A bridge is a structure usually horizontal, not always, but usually horizontal and straight, that connects 2 points, allow to overcome an obstacle. Now, in this case, the bridge can be either for vehicles, can be for people, can be a mixture of both things. There are a wide range of typology of bridges. One of the most common, above all, if we are talking about steel in general, steel realm, is the truss bridge. What is a truss bridge? A truss bridge is a structure that is mainly working in its full height. So imagine to have a full beam. The full beam works because it has a lot of material. The idea of the truss is to take that design that is pretty inefficient because we have a lot of the material that doesn't work for the purpose that we want it to work, and remove it. So to try to make a structure that is still functioning pretty well, but is much more lighter and much more manageable in difficult conditions. So that's why we have the truss. For the truss to work, of course, we have a simple beam. A combination of beam can be a truss. And if all the beams are in the same plane, we have a 2D truss. If we have a combination, a multi-planes, so a series of multiple truss connected together by transversal members, we have a 3D truss. A typical typology for a beam is a tube truss. So you have a structure that is enveloped in a box, and all the trusses are on the four edges, and they go straight. Why this? Because what happens is for the type of loads that a structure like this is subjected to, the structure has to have the capacity of resisting the torsion. So when the structure tends to deform, it has to be able to deform. Try by yourself. Take a plane like this and try to twist. It's pretty easy to twist.
It
While
is.
if you make a circle, if you close it and try to twist this, it's much more harder to twist. So this is the principle why we have a closed tube, a truss tube bridge. Well, let's start from the definition of the truss. And now, for avoiding to waste time on useless points, let's put a template that works pretty well because we can modify eventually the template as you wish. But let's start with a template that let us skip all the boring points of the modeling itself. So we will start with a truss bridge with a template, vertical truss. We can do different typology of truss, slope truss. This one is usually one of the most common. So let's go with this truss and let's design, I don't know, 10 base, height of 4 meters. Now this we should go a little bit more in detail. It's very important, and this one is a point that
Have you designed anything? Because I can't see anything in my screen.
I didn't design anything yet.
Okay.
I haven't designed anything yet, but you should be able to see one thing, to be able to see a kind of pop-up window. Can you see it?
I can see the sub window in
Yeah.
white. That's all I can see.
Okay.
Oh, now I can see
What can you see?
something coming up.
Okay. So I was making a different point now. Since you were not able to see it, I had to build these things. But what I was saying, when you are in the definition of the structure, one of the things that SAP asks you to put as an input is the height of the truss. Now, the height of the truss comes from a pre-design. What do you have to do? You have to take the length of the beam, the length of the bridge that you want, right? We are
Right.
assuming that is a truss in this case, but what we have to do is we take the length of the bridge, we apply the pretty much the typical load that we think that it can go on the bridge itself. We calculate the maximum bending moment. We divide the bending moment for the height of the truss, and we see what's the tension force and the compression force that goes in the two truss. If this tension compression force leads to a section, a steel section that is reasonable, we are good and we can proceed with the detailed design. Or the other step is that this force leads to a section that is too big. So what we are going to do, we just increase a little bit the height of the bridge.
Sure.
Following?
Yeah.
So for the moment, I mean, this one is the first step. We'll see. We are designing a 30-meter bridge.
30 meters.
Now,
Okay.
30 meters bridge. Now, for 30-meter bridge, unless it's a pretty heavy structure, I think that this height is a little bit too much, but we will go and check this. This one is now 4 meters. It's pretty much. As a rough idea, you have to have approximately a span. So the length of the bridge divided by 30, 35. Depends from the type of structural system that you want to use. So we are roughly in the same in that range, right? Here we are about 25, 30. Okay, so we take this, we replicate in Y, and we make, I don't know, a 10-meter bridge, 10 meter wide. And we replicate once. Okay. Then what we are gonna do is, so this one represents the main structural element, the main supporting element of our bridge. Okay, so those are the primary structures. Then we will connect all the transversal member, the secondary, and we replicate these as well from here to here. We say 3 meters roughly. Okay, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And apply. We replicate like this. And the same thing here. We put this beam and we replicate this. Replicate from here.
So you're pretty much designing the floor, and you're pretty much designing the floor and the roof.
Now we are not designing anything yet. Now we are just putting things together.
Okay.
So this one should be 8. All right. So this is pretty much the shape of our building, of our bridge. If we remove the grid, and we can see that in 3D. So now are pretty much the sections, the default section that they put. When we design a bridge, one of the, of course, there are few aspects that are peculiar to this structure. Of course, we have to make sure that if a certain number of people in the static condition, it means just people standing on the bridge, are all there, and the bridge is full of people, the bridge has to to resist from a strength point of view, from the strength point of view. The other thing that we have to make sure that this is a general for every type of structure. So not only we have to make sure that the structure has the real capacity of sustain the load, but we have to make sure that under a specific load, the structure doesn't deform too much, because the deformation can cause other issues. For a building, a huge deformation can cause problems, cracks in the partition walls, for example, or in the ceilings. For a bridge, a big deflection can cause a problem for the drainage, can cause a problem for the lights that are installed to the bridge, these kind of things. So the strength of the bridge is the paramount. Then we go with the deflection. We make sure that the deflection are not excessive. And another extremely important thing for such type of structure like bridges, for example, is the dynamics. How the bridge behave under a repetitive load, a dynamic load. So what I mean by that, imagine that you have a group of people that are working on let's talk about pedestrian bridge, but it applies the same way in vehicle, with some, of course, physiological differences, but it applies the same way to the vehicular bridge. Let's start with the pedestrian bridge. Let's imagine to have a certain number of people that are working all together, and they are working on the same pace. Doom, doom, they are marching. What happened to the bridge is that is subjected to a cyclic excitation, right? Boom,
Yeah,
boom,
yeah.
boom, boom. Now, every structure has a particular characteristic under dynamic, particular value that is pretty much the indication on how that structure behave under dynamic loads, and it's called the natural frequency of the bridge of the structure itself.
Sure.
So the natural frequency is the way in which, if you apply a small perturbation to the bridge, that starts to vibrate, and the vibration is characterized by the frequency, and this is the natural frequency of the structure. The frequency of the structure, it depends from the type of bridge that you are designing, the restraint of the bridge, how that bridge is particularly supported by the surrounding environment, the mass of the bridge, so the weight of the bridge, and the connections. Okay? And the material, of
Okay.
course.
Yeah.
Here we are talking about steel, so the material is intrinsic. Now, if the external loads have a cadence, a frequency that is close to the natural frequency of the bridge, a very bad phenomenon occur, and is called resonance. So it means that even if the load itself applied, the magnitude of the load is not big, but because of the typology of load applied that is dynamic, and it is very close to the natural frequency of the bridge, what happens is the excitation on the bridge, the stress on the bridge, it will grow exponentially. So even a small amount of force, of load, can lead to a catastrophic failure of the bridge. And this is the reason why, I don't know if you know this, this is the reason why the army, the guys, the military, stop to march when they cross the bridge, because they want to avoid the catastrophic failure under resonance.
Yeah.
So platoon of army stops to walk in synchro because of this problem. So um, so yes, this one is a very, very, very important topic to take into account, a very important aspect to take into account in the design of bridges, in long span structure, and in general in every structure. Of course, there are some structures that are more vulnerable to this type of things, like slender structure, very slender structure like these are more vulnerable to these dynamic loads, while a huge concrete structure is less prone to have problem under that type of loads, even though it's always important to have a look to this. This is to say that we don't have to stop ourselves in just uh, checking the capacity of the beam and say, okay, our job is done. No, our job is done when we are able to make sure that all the aspects of the design are covered, uh, and and the design itself is satisfactory in terms of constructability. So when we start design, when we start any type of design, the very first thing that we have to do is to put a concept together, and
Yeah,
then we have to ask ourselves how these things can be built. Because we have to remember, as an engineer, the main goal of your job is to let this concept that you are putting together be built by someone somewhere.
exactly.
So the very first question, the important question that you have to ask yourself, how this structure is going to be built. Is it too heavy to transport? We can build in pieces and bring in pieces together. Do we have to make sure that all these pieces can be supplied in a proper way? In a bridge that now this is a very small structure, but imagine a structure that has, I don't know, 2,000 members.
Yeah,
Is it better to have 2,000 different sections to optimize every single member, every single beam, or we can get rid of a little bit of efficiency, but we try to reduce the number of special pieces that they have to do. So we try to reduce the number of members, the number of sections that they are gonna supply for that specific structure. So those are all questions that, unfortunately, when somebody approach a design, usually that there are extremely good engineers, but usually is something that is not asked. Is something that is not covered. And for a good design, I mean, everyone can go in the project, build this simple model that I built here, click this button, and say, okay, this is the design. Everyone can do
yeah.
that. So that's not the design.
That's
It,
dangerous.
it, yeah, I mean, cannot be dangerous. Cannot even be dangerous, but can be. First, it could be dangerous. It could be extremely dangerous. But if it is not dangerous, it could be extremely inefficient, because if you build a structure that can weight, for example, if we measure the weight of these things, probably is 4 times what it should be.
Yeah,
So yeah, those are pretty much the very first thing that you have to ask yourself. Then then another important aspect is to try to link the structure with the architectural needs. Now, this things is one of the most debated topics in the engineering world, but it's extremely important that there is a very strict connection between engineering and architecture to make sure that what we are delivering is not only safe, but is pleasant to see. Is how to say is aesthetically acceptable at the very least. Because usually, in my experience, engineers are very good in put numbers together, but are very bad in putting something that is, is graceful to see. While the architects, while the architects on the opposite side of the spectrum, they are very good in putting fancy idea everywhere, but they forget that we live in a world in which we have a 9.801 meter per second square gravity that is acting on the structures. On the paper, every structure works. In
Exactly.
reality, not all of them work. So, yeah. Now, regarding the load themselves, for a structure like that, I will go the other step. If you want, we can continue a little bit, but then it's from now on it will be pretty much the boring part, because the other thing that we have to do, we have to apply
The
some
boring
loads.
part. And see
Yeah.
the limits.
Well, I mean, first of all, we have to make sure. First of all, we have to make sure that these things is standard. Okay. No, we replicate these 9 times as well. Those one are the load patch. Now we are gonna design. We are gonna put not what we're gonna do is that is a fair, reasonable assumption itself. Now, in general, for this type of structure, the deck, that is the horizontal part of the bridge, will work as a composite between steel and concrete, right? So we should have the steel beams that are running through, and then on top of those steel beams, there will be a slab that which will act in conjunction with the steel beam. So altogether, they form the membrane that we are gonna do, right?
Right.
So let's assume that we are gonna do exactly this thing. Now, the other thing that we have to do, we have to put probably, now we said that this one is 10 meters wide. So what we should do is we have to add some intermediate beams on this. So we are going to do this. This is our primary structure, okay? The two trusses on the side. Then we
Sure.
have secondary structure that are the beams that are transversal, and that they are called secondary structure. And then we will have a tertiary order of beam that will go from here to here, that are required only to reduce the
It's
length
fun.
the span of the slab itself. Oh, let's do that. Edit, replicate, pick the point from here to here. Let's replicate from here to here, minus 10 divided by 4 divided. All right. So now what we have to do is let's apply some load here. We will define our first load cases. So dead load. Now, regarding the dead load is automatically calculated by the software, by the program, but there are some aspects, some elements that the program cannot take into account. For example, when we are talking about this one is mainly in steel. When we are talking about steel structure, we have to take into account the weight of the connections. Now, the weight of the connection can be pretty consistent. So what we have to do, we have to increase a little bit the self weight of the structure itself to take into account for the bolts, for the welds, for the other plates that will be used for stiffening, these kind of things. So for a structure like that, let's put 1.2. So it means that 20% of the weight of the structure is for the connection.
Okay.
Okay. Then we have SDL, and then we have 0 here. We add as a dead load for the combination, and then we have live load. Here is live. Add. On this, we should calculate the wind. We should calculate the earthquake, but let's put some wind. Just wind, just to see the application of wind as well.
Okay.
This is wind, and then we can put EX other.
I can't see anything you are doing.
I don't know why these things cannot does not show up. Let me see if I share the screen again. Hold on. No, it doesn't show the additional windows.
Yeah, I can only see the truss is there.
The main window.
Yeah,
Okay.
only the main window.
But it's pretty a shame because you cannot see all the definition of these things. All right. Let me quickly assign these things, and then we will go to the result directly, and then we will because unfortunately you cannot see what I'm doing.
Yeah, no. Um,
Yeah, you don't really see what I'm doing. So I don't know. Maybe we can organize for the next time. This kind of activity is something that we can organize for a future time in which I can
okay,
we
that's okay.
can see how we can do this. Because it's a shame. I can go ahead for another hour, but you can see what I'm doing.
It's okay. Let's go for the
Uh,
results and see how the structure is going to behave.
let me add some. Let me add some load and let's see. Assign. Area section. Modify. It's pretty a shame that we can see what because there is not much point on doing this. Define, assign. Now I'm trying to assign some quick loads to see what's going on. So what I'm assuming is I'm assuming 0. I don't know, 1.5 kPa for the superimposed load, and I'm assuming, of course, 5 kilonewton per square meter for the live load. And here we will assign some wind, assign some wind, frame loads, distributed wind in the y direction. Here we can go with, I don't know, let's go to a wind area. Let's put 7 kilonewton a meter of wind. It's pretty a lot, but let's put like that. Then the other thing that I wanted to do is let's define the load combinations. So for designing the load combination, we have to decide which code we want to use. Let's use the Australian code. Let's consider the deflection as well. Yes. And then we go select design combo. Automatically generate the combo, define, and automatic design combo, steel frame, select load cases.
Can you make this window smaller so we can see whether I will be able to see the other windows?
No, but it's not another window. It's a pop-up window that is coming from the program. It's not two separate windows.
Oh,
I'm
right.
clicking
Okay.
on the program itself, and
Right, right. I got it.
yeah, yeah.
I get you.
So that's the main problem. I'm just quickly check the combinations to see if everything is appropriate. It seems to be modifica. Yes. Yep. Yep. Okay. 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 Now what we have to do is design, select design combo. Yep, this is correct. This is correct, okay. Let me save this thing. New folder. And I hope that you are not getting too much bored.
No, it was just going to be more interesting to see
I know, I know.
the inputs that you are
I absolutely
doing.
know. So okay, things that I have to do is assign. Now the other I assigned the load, I applied the load, I defined the load combinations. Now the other thing that I have to do, I have to make sure that everything is meshed enough to try to approach to the right behavior of the structure. So I have to subdivide all the elements in order that they can work together. So assign, and we are gonna do this. Yeah, you cannot see anything. So it's I'm talking about fried air. 0.5. apply side area edge
So you pretty much
release.
applied the loads, you did run the structure, and it
I
says
didn't
that,
no, I didn't run. No, I didn't run. I just defined the loads, defined the load combinations. I applied the loads, and now the things that I'm doing is I'm meshing the structure in order that when I run the analysis, it runs properly. The results are more accurate. You
okay,
know,
yeah, I do.
automatic area mesh. Now SAP allows you to automatically define the size of the mesh that you want to apply. And I'm doing this automatically now. I'm applying the same. I'm trying to apply the same discretization for the members and for the mesh. In order when these things will run, everything is pretty much connected together. Now, the other thing that I have to do is, if you see here, when I select this, probably this one is something that you can see. When I select this element, you see that it's spanning between this and this. Now, what I want to do is that instead to spanning between this and this, it has to span between here and here, between here and here, between here and here. You know?
Yeah,
So I have to take this and subdivide. Define, edit lines, edit areas, divide. Okay, so you see now. Now the other thing that I want to make sure now for the structure that we are designing now, we wish that the loads are pretty much going between this member to this member. So this member to this member to this member, from this member to this member, from this member to this member, from this member to this member. Then those member here will transfer the load to this member and this member, right? And those member
right.
here will transfer the load to this member and to this one here, right?
Okay,
So
yeah.
when we apply the load, we want to make sure that the main direction of the loads are this, then this, and then this. Okay,
Yeah.
so for doing this, I have to check how these elements oriented. Now you see the red arrow.
I do.
The red arrow is the direction in which the load is applied, because I apply the load say in such a way that he's gonna put the load on that and redistribute on the two edges, right?
Okay.
But
Yep.
now what happened is, since this one is oriented with the red arrow this way, the load will go from here to here. I'll show you. For example, I'll show you an example. Display load pattern, the area uniform to frame resultant, apply. In that there is nothing, so let's go with, so you see,
Yes, I do.
yeah. So what I'm gonna do right now is I'm gonna select all of these and change the orientation of those elements. Define, assign area, local axis, and we rotate these things of 90 degrees. We apply this, and then when we go and we show again this, we change the orientation of the loads.
All right.
Okay,
So you just
so
Yeah, they
So
are in
what?
the biggest span now. Yeah, they're just going the
Yeah,
other way.
yeah. So now the other thing that I have to do is again to make sure that everything is framed correctly. Sign frame area automatic mesh 0505. Okay. Now the other thing that I have to make sure, we said before that the beams should act in a composite action with the slab itself, right?
Yeah, right.
So for doing this, we need to do this. I'll show you something. Now, can you see here how the beam is located to respect the slab? The beam and the
Yes.
slab arrive in the same plane. So they are, you see, the beam is sticking out from the slab. This is not
Yeah.
the situation that we want. We want, I'll show you
What
something.
do you want?
We want this. The sign frame insertion point. Top, center, apply. You see how the beam changed? They shifted down.
Yeah, I
Now, this
do.
is not enough because the slab is still halfway to the beam. So what we have to do is we have to rise up the slab itself.
Sorry, why do we need to raise up this lab?
Because what happens is if they are in the same plane, they don't act compositely. Each element acts on its own. While if you take the beam itself and you put the slab on top, when the beam try to tend to bend this way, there is also the slab that will give a contribution. So the resistance of the beam and the slab together gives you the real resistance of the structure.
Okay.
So we have to rise the slab as well. Area. All right. Now the slab thickness that I use is 180 millimeters. So it means that we have to rise these things up of half of that, which means that we have to do 90 millimeters up, 90 millimeters up, 90 millimeters up, and 90 millimeters up. Apply. I put 90 meters. I have been great because I usually work in millimeter.
Yeah, I can't see this lab anywhere.
Yeah, I know because I put 90 meters up.
Okay.
Now I have to modify. Here we go. Okay.
Okay.
Now everything should work properly now. Save and run these things. Now here we have to go pretty much in detail of what's going on, but now you see here the structure itself is deflecting 105 millimeters. Can you see that? 105
Okay, yeah.
millimeters
Yeah, yeah.
under the self weight.
Yeah.
105 millimeter, it means that if we take 30 divided by 105, So 30-meter length, right? 30
Right.
meter was the length, the total length of the thing. The deflection under self weight is 105 millimeters. So it means the deflection is L over 285,
Okay.
which is not bad. So we are
So sorry,
pretty
how
good.
much is that? How much is L by
If you take L and
300?
you divide it by 285, 200,
200.
the limit is, it depends, 250, 300, it depends. It could be, probably we have to stiffen this a little bit. But what we are going to do is we are going to run the check of the steel member. Now, all the members are the one that are from default. I didn't change anything yet. What I want
Okay.
to do is want to have a feeling on how the structure will behave. Now, what we can see here is that the beams that are composite with the slab will work,
Yeah,
are
okay.
working pretty much. All the
Yeah,
other
okay.
beams are failing.
Yeah.
So what we have to do is we have to do
To-
a proper design of these things.
we need to
You know,
increase the section.
yeah, we need to increase the section. Now we could do this in several ways. Of course, we could have done a pre-design and we could have put directly the section in the program. Another thing that we can do is to do this. Um, Still you cannot see, but we can assign automatically. We can say to the program, find the optimal section that allows me to pass all the checks. So what I'm going to do is define frame section, new section. I have to import, we want to use open section, right? We are going to use open section. So I-beams, Australia, New Zealand. We are going to do this. We are going to select all of them. For the moment, we don't care about the material could be this. Okay. Add the new material, add the new frame. We are gonna do other, sorry. Add the new property, and then we have to do other, and then we have to do section designer. Design type, general steel section. Import the new property here. Section designer. Seriously, add the new property, add auto list. We are going to assign all of these. Yeah. Okay. Okay. Define frame section. What did I do? Out. Okay. And gel. Assign frame section. Now this will take a bit, but so you can see that now everything is changed. What I did is I define a list of sections,
Yeah.
and the program is gonna pick in this list in order to achieve the full design.
Okay.
Let's remove the extruded part, maybe it will work a little bit better. Let's remove the slab, not in view, maybe it will work a little bit better. And let's design this thing. It will probably take a bit of time, but maybe not that much.
So now the program is just changing the sections.
Now the program is changing the section. What is done usually is that you tell the program, this is the list of your sections. Automatically assign one of them and start with that. Do the analysis and tell me if this section fails or not. If
Okay.
if the section fails, change it. Go with an additional section. Now the process is an iterative process. Why? Because if you change the section, you change the self weight of the structure, so the load change. So you have to repeat this. We have to finish. We have to repeat these things several times. But for the sake of these things, we will try only one, and we will go with this just to show you all the steps. We are pretty much almost done. So
Okay. Yeah. Now the program is pretty much doing what we used to do in uni, analyze every single section and then change it.
the
Get
program is doing what I should have done since the beginning. The program is doing what I should have done since the beginning. Now, okay, here I have done a very broad things. I put all the sections. Now, it's not something that you usually do. You choose a certain number of sections, and then you go with them.
Yeah.
You see, here we go. And this one is the design now. Everything is satisfied. Now, this one, I didn't include this for the moment, but let's forget. Now, as you can see, everything seems to be fine. Now, let's see this section, what section he decided to have. You cannot see from there, but okay, the section that he decided to assign since the beginning was a 700 WB.
Okay.
The design section that he thinks that is required for this type of analysis is 273 HP, is another type of section. So now, to make the process running properly, I have to delete the result, rerun the analysis. If the previous section are equal to the next sections, the process is complete. Otherwise, I have to rerun again. I have to rerun this process again until the sections at the previous stage and the section at the actual stage are the same. And the project and the design is done.
All right.
So yeah. And this is the design of the project. Now, I gave you a bit of an insight on what it should be done, and this one is how it should be done. Now, the other thing that you should check, and it's very important to check, is the mod shape of the structure that tells you how this thing is acting dynamically. So here, just to show you one thing. Now, you see this number.
Which number? It's 3 millimeters, is it?
No, this
I
one is
see
3
three. There
hertz.
is no 3
3
hertz.
hertz. 3 hertz. Yes.
Okay, so it's
Now do you?
the frequency of
Yeah.
the first model,
The
is it?
the first mode shape of the structure has a frequency of 3 hertz. It means that if you are running on this bridge at 3 steps per second,
Yeah.
you're gonna make this bridge vibrating too much.
So this is a shit bridge because
Well, no,
nobody can run and nobody can run on it.
No, but the design is not complete, of course. This one, as it is right now, is a completely useless bridge,
Yes.
as it is now. But I remember, I want to remind you something. In London, one of the most
Yeah.
iconic bridge has the problem that I'm telling you now. The Millennium Bridge in London has been opened with this problem, and what they had to do afterwards is they had to install some device that will reduce the vibrations after the
Okay.
opening.
After the
So
opening.
after the opening, so people were
And it's
running
a
on that.
huge bridge.
That's pretty huge bridge, but people were walking, running, and so on that bridge. And only after that, they understood that they had to put some additional device to dump those vibrations. So this is a shit bridge, but it's not uncommon at all to have bridges or structure that behave this way in real
You mean
life.
bad bridges? So we have many bad bridges.
We have many bad bridges. Yes, we have many bad bridges, many bad structure that are good for just one purpose, not for all.
Okay.
Okay, so that's pretty much it.
Okay. So what's the solution? Should we change the engineers who are designing the bridges?
No, the solution is that we have to put more time because this thing shows that you cannot make a design of a structure in 10 minutes. There is no way. You have to think about that.
Of course, it's not a pizza.
Yeah, the pizza need require 3 minutes. So if you make a pizza in 10 minutes, it means that you are making a shit pizza. If you make a design in 10 minutes, you are making a shit design.
Yeah.
So as
So
simple as that.
okay, so to fix the not the mistake
There is
to
no
fix
mistake.
this
Here, there
bridge
is no mistake.
to fix
There
the
is no
bridge
mistake.
to fix the
Yeah,
problem. Well, three to fix the problem of the frequency. Which
yeah.
frequency should we have?
We should go at least above 5 hertz.
5 hertz. How do we get 5 hertz here?
The one way could be probably to use a lighter section and to reduce a little bit the span because now I consider 3 meters. Probably if we go with 2.5 between here and here, we reduce the problem. We remove the problem. We have to make these things a little bit stiffer.
Can you change the span to 2.5 now so we can see if we fix the problem?
No, I cannot.
Is it?
It's not that easy to change. Right now, let's see.
Oh, it's not
Yeah,
that
okay.
simple.
I mean, no, it's. Let me think. Because what? Let me see. Because if I reduce to 2.5 or whatever, I have to add another one. Let's see what it can be done. Um, no. Okay. Okay. You know what we can do here? I'll show you. Because I didn't change these before. What we can do is those things are 10 meters anyway, so a huge span as well. What we have to do is we assign a different section for this because now I thought that even the section that I used for this was a huge one, but no, it was not. So if we go with, I don't know, let's go with 800 WB. Let's see. Let's see what I put here. You see?
Yeah, what did you change? I didn't see anything changing.
The section of this beam.
Oh, you changed the section. Okay.
Yeah, because when I did all the design, I didn't change this section. I
Okay.
made all only those section here change. So now I change the other one. Let's see. We are almost over. No, we haven't solved the problem with this. Let's see. Yeah, we haven't solved the problem. with this. So probably we have to make everything a little bit more stiffer. Probably we have to make these as well stiffer.
You mean the main structure?
Yeah, probably the main structure. So one way could be to have a cable or a strut that goes from here to here that is
Yeah,
connect
okay.
the top cord. Um, the other way could be a tube. We could use a tube, but yeah, I mean, we have to do something. The other way could be to increase a little bit the height. That's the height could help. The height itself could help. And it move 1 meter up. Now, of course, all these this section they have to change accordingly, but no, it's just too heavy. This one is just not the right topology for this type of bridge.
It's not the right what, sorry?
It's not the right typology. Probably we have to go with a different typology, or we have to make this thing stiffer. Probably, I don't know, changing this element here, this element here, and this element here are a little bit too. Side. 800 WP, for example. Let's go apply. No, no, because what is the problem here? And I will show you something. We haven't solved the problem, not even this way. What's the problem here? The problem is that the deflection of this point is not
Too
stiff enough
much.
here. Yeah. So we have to make this. That's exactly the thing. Now I put 30 meters. Probably this type of structure is good for 20, 25 meters. No, something like that. So we can fix it, but we have to go and make modification. Probably if we go with tube here, maybe something that we can go with. Assign frame sections. Now I'm pretty much throwing number.
Yeah, I do. It's not how you solve the problem, right?
No, usually you won't solve the problem in. You don't solve the problem this way. No, we have to avoid. You know what? Yeah, not even this. So this one is not the right topology for the bridge. It's just inefficient. Because all of
Okay.
these changes that we have done didn't really change the behavior of the structure. You know what will change the behavior of the structure?
What?
I'll show you something. Let's go back to the previous. Well, forget about the previous. Here and here, here and here. Side, restraint in the. You see, now we started to to change. Now we are almost
Oh
more than
wow.
4. Huh?
What did you do?
I put some restraint here and here. So I imagine that I could put a strut that goes on the ground or goes in a tower or something like that.
Okay.
So, now we are a 4.7, 4.1. Now, 4.1 is already acceptable. It's not the best, but it's already acceptable.
What
Because
if you
now you have
do
to,
the same thing in every single point?
no, because I mean, you can put, what do you mean in every single point?
Well, because you assumed that you're gonna have some cables uh,
Yeah,
at the
I'm
beginning
assuming that
and
I
at
have
the end.
either a cable or a strut or a fix something in a tower. If I have a tower on the two sides, I can fix the
Yeah.
structure into the. Yeah.
What if you what if you do
But
more
okay, now
than
what I want to show
two
you,
elements?
I want to show you one other thing. Now, can you see here the shape has completely changed. Now we are not caring about this shape. We have to care about the shape that gives you vertical deflection, like before. Do you remember that before was curved this way?
I do,
No.
yeah. Yeah.
Yeah, so that one was the frequency that we are caring about. Now this one is 4.7, but 4.1, but it's not the frequency that we are looking for. So we have to go. I'll show you something. Uh, this one is still not the one because it's moving sideways.
Okay.
This one is still moving sideways, but it has a bit of deflection here in the middle, right? So
Right.
now what we have to do is not only to check the frequency here, but how much structure is contributing to this. Now we are going to a complicated thing, but another thing that we have to check is model information, and I'll show you quickly this, and then here we can conclude. Now we have to make sure that if we are designing only for static action, that this is above 85%. This one is 97, so this one is good. Okay. Are you
Okay.
following me? This number. This one
I
means
am, yeah.
that 97% of the total mass of the bridge is contributing to the dynamic behavior of the bridge itself. Right? Now,
Right.
then we have to go to participation ratio, and we have to find here. This one is what I wanted to show you. Now, the first mode that we have to really care about is this one here, is the third, that has a mass of 78% of the full structure. So we have to make sure that this one, the third mode, which is 4.5, is pretty good now. Did you get the point?
I think,
This one
yeah.
is a complicated topic. It is a complicated topic, but yeah, we have to be careful on what we are looking at. It's not always the first number that we see, you know.
I do.
So yeah, even in a simple structure like this, there are a lot of things to take care of.
Yeah. Simple structures, they have particular problems.
Yeah, exactly right. So yeah, and this is pretty much it. What do you think?
Yeah, no, nice. That's a nice analysis. What would be the next steps?
The next step will be to reduce a little bit of the weight of the structure and to make sure that everything works properly. Now, the other thing that I have to check is this is pretty much the design that I will consider. Now, what I will go is I will check the weight of the structure and to compare with a standard construction. Now, for example, a structure like that, I'm expecting that weight for people. I'm expecting a weight of, I don't know, 110, 120 kilograms per square meter. If I'm not in that weight, it means that I have to, to improve the structure itself. Maybe changing the height, maybe changing the section, changing the typology, to do something else.
I do.
And then when I have done all of this, I have to go to the architect and I have to say, this is my design. Do you like? They are going to say no, and I have to start all over again.
So they will never like the first design. That's what you are saying.
No, because they usually say, okay, but can we start to avoid all of this? So a design that they would like, for example, would be this. Design that they would like is, I'll show you a design that they really would like. I hope that there are no architects in your audience, because otherwise I will start with a lot of enemies, right?
I'm pretty sure that we will have some architects here. Architects, don't get, that's not personal, right? That's
No.
just
It's not personal. It is what it
that's
is. I
just
mean,
something that happens in real life.
yeah, this is a
And
structure that
I'm
they
pretty
would
sure they
like.
know that.
This is a structure that they would like.
Really thin.
Yeah,
Really thin.
yeah. And then they say, okay, this is the structure that the architecture that the architects would like. Then, if you go to the construction company, they will say, okay, but can we do this? The construction company will say, okay, can we do this?
Well, in this case, what do you say? You ask if they believe in God, because not even
Yeah.
God's gonna be able to save this
No,
structure.
I will say, okay, if you want to install these things on top of the building and nobody is gonna go, yes, of course you can go with this.
Yeah.
And instead, the structure that we like, I'll show you the structure that we like. If I have to design one structure, I will put this. So just to show you the three different views from people. This is the structure that I like.
Jesus. That's too much.
Yeah, but it's safe.
And it is expensive.
Well, I mean, compared to what? Compared to one of the bombs that
Jesus.
they're putting?
10.8. Huh?
The what?
10.8.
Yeah,
The frequency.
yeah. So this is a structure that I like. And on this, we can even remove these things. Aside, we can remove these things. Put 3 here. We can remove the things that I added before. So the bottom line here is, as a structural engineer, if they give you a design, it's better that you start from something like this and you go backward. Because if you start from something that is more rational, then we will arrive to the structure that I showed you before with missing bracings.
Yeah, right.
So you start with this, and then I say, okay, now I have a lot of margin to operate, because the main point for a job is, you see, that's just perfect.
Yeah.
But the
Well,
main
how
point
are they
is,
gonna?
no, okay,
Which
imagine this.
profiles are you using there?
1,200.
Yeah. How are they
Now
gonna
imagine this,
1200?
Leandro. The point is, if a person, a, a specific person in the world decided to do a job, no, and he
Oh,
has
yeah,
the money to do the job, and you tell them this bridge costs $10, right?
you're right.
At the initial design, you tell them this bridge costs $10. They will
Oh,
say,
yeah,
okay, we will go with $10. If during
yeah,
the design, this bridge, instead of costing $10, it costs you $12, is a huge problem.
yeah,
If you go to the
20% more.
client, yes, if you go to the client and say this bridge costs $15 at the beginning, but during the design you make the design of $14.5, everybody's happy. Did you get my point?
Yes, I did. I do.
Yeah. So that's the point. Is a very real balance. You are really running on a very narrow street, and it's not, you know,
Yeah,
there is a lot of balancing work to do.
I I,
That's
I
pretty much it.
understand. It is.
Yeah.
Um, what else would you take into account when you are doing this type of analysis?
Conceptually, I pretty much told you everything that I will take into account. Now, the other thing that I would consider here, as I mentioned before, is how this thing is constructed. Then this one is mainly necessary when I start to design the connections. But the stages, the mental steps are all the one that I give you. From a conceptual point of view, the design itself is complete. We have done a design from start to begin with all the aspect covered. Now the next step of this, once we have designed the profile, once we agreed the profile, once we agreed the criteria that we want to extend, the next step is to design the connections, to give them a methodology for building the bridge itself. And if there are some other requirements, that could be hydraulics, can be fire requirements, fire protection requirements, it could be seismic. Here we didn't consider any seismic, we consider seismic, but that's another thing that is more detailing. Uh, but conceptually, again, from a conceptual point of view, the design is all here. There is no many other steps that you will take. Coordinating with the architects, the first thing. Coordinating with the architects, so decide which type of build or bridge do you want. Then with the client for the requirements, because if the client says, no, okay, I want that this bridge deflects 400 millimeters, for example, you can say, okay, it's your choice. I give you all the tools for you to decide. If you tell me that you want that bridge that is deflecting that much, for me it's fine. So it's a choice from the client. So you
No,
decide
no,
that
no,
with
no,
the
no.
client.
But it's your responsibility to make sure that
No,
it.
no, 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 no. No, it's not my responsibility. My responsibility is that thing should be safe. If the client wants to save money, I will put on writing that he wants to save money, and the deflection criteria is up to him.
No, but as an structure engineer, you can't send
No, but
a
it
design to the
works.
construction site that it's not gonna be
No,
that
I
it's
have
not
to
gonna
make sure.
support
No,
the loads.
I have to make sure that the loads are fully supported and the bridge doesn't collapse. But if the client tells me that he wants to save money, I will put on writing that he wants to save money, and the deflection criteria is up to him.
Uh, guys, I'm just having a problem here. Iuliano will be back soon. Guys, we are having a technical problem. Pretty much everything that was explained here was what we planned to show you today. I hope that all of you who are into the construction field, engineering, architecture, building design, I hope you really enjoyed it. And I will let you know when I'm going to have my next guest, or I will also let you know when my next episode is going to be. I will just get Iuliano back to the stage so he can say bye to all of you. Hey, buddy.
Here we go. Sorry, I mean, problem with internet.
That's okay. Look, I've just told my audience that we have shown them everything that we were planning to show them today. And I would like to thank you as well. And I would like to open this last minute for you to talk to my audience. And again, thanks a lot for coming.
Thank
That
you.
was
Thank you for
awesome.
having
That
me.
was awesome to see, how you design, what you need to think when you are designing a simple structure as a small bridge.
Yeah, thank you for having me. I hope that that one will. I mean, next time we can do something a little bit more structured if you want. If there will be a next time, knowing you and the preference from your audience, if there is a suggestion.
I
Now,
can't hear you.
huh?
I can't hear you.
Can you hear me now?
I can.
Yeah. So yeah, next time if there is a next time if we organize another podcast like this, we can go a little bit more in detail. Now it would have been good to give you an overview on what's the approach.
Sorry, you wanna give me an overview now?
No, no, is what I gave you was a kind of an overview on what the approach is. Next time we can go more in detail. We can go a little bit more in detail on what I described as model analysis, frequencies, this kind of things. If it can be of any interest.
Okay.
Yeah.
Okay. Yeah, it is. Let's plan for that. And for now, thanks for everything.
Thank you. Thank you, guys.
No worries. Thanks everybody. There was one more podcast. I will let you know when my next episode's gonna be. Have a nice evening, morning, afternoon. I don't know where you guys are right now, but I wish you have a good time. Thanks, Juliano. I'm gonna finish the stream now.
Thank you,
Bye
guys.
bye.